Many of you have probably heard of magnetars, but what exactly are these magnetars? What are the characteristics that make them so dangerous, even placing them among the most dangerous stars in the universe? Today, together, we will descend all the way into the cores of these magnificent stars and try to understand each and every one of their features. But before we move on to our video, if you love this kind of content, don't forget to subscribe to my channel, like my videos, and state your thoughts in the comments for new video ideas. If you are ready, let's embark on a long journey toward magnetars. First of all, based on our current observations, magnetars are celestial objects that possess some of the most extreme physical conditions known in the universe. Of course, defining them merely as highly powerful or highly dangerous stars would not only be insufficient for people to understand them, but it would also be a great injustice to magnetars themselves, because magnetars exist in a regime where matter, energy, and even the vacuum of space abandon their accustomed behaviors. When looked at from the most fundamental level, these stars are actually a type of neutron star. However, the magnetic field they possess is so immense that it is necessary to place them into an entirely separate category. If we want to talk about the birth or formation of a magnetar, we actually need to look at the death of another massive star, because the formation of a magnetar begins during the dying process of a giant star. According to estimates, a star at least 8 to 10 times the size of our sun generates energy by undergoing nuclear fusion in its core for millions of years. It converts hydrogen into helium, then into carbon, oxygen, and heavier elements. However, after a certain point, iron begins to form in the core. Under normal conditions, iron is an element that does not produce energy through fusion, and past this point, the iron begins to weigh heavily on the star, rendering it unable to support its own weight. The core collapses instantaneously. Atoms are crushed, and electrons merge with protons to turn into neutrons. One must not overlook the fact that this collapse happens so incredibly fast. Roughly speaking, it occurs within a tiny fraction of a second. As you can understand, the speed of this collapse is immense. During this collapse, a staggering amount of energy is released. Subsequently, the supernova explosion occurs, an event we all know or are at least familiar with from science fiction movies, and the outer layers of the star are blasted into space in a giant explosion. The remaining core is now a neutron star. The most striking feature of this neutron star is its unbelievable mass relative to its size. Think about it this way: an object with a mass averaging 1.5 times that of our sun is squeezed inside a sphere only 20 kilometers in diameter. Because of this, you constantly see claims on social media or in popular space documentaries stating that a teaspoon of a neutron star would weigh more than Mount Everest. This is exactly where magnetars come into play. However, first I need to clear up a common confusion. Not every neutron star is a magnetar. For a neutron star to become a magnetar, two things must be at extreme limits at the exact moment of its birth: its rotation speed and its magnetic field production. If a star is spinning incredibly fast as it collapses, which corresponds to a speed of rotating around its own axis hundreds of times per second, the electrical currents formed inside it generate an unbelievably powerful magnetic field. The magnitude of this magnetic field is staggering. To put it in a more understandable way, the Earth's magnetic field is very weak and can be measured even with a simple compass, but a magnetar's magnetic field is approximately 1 quadrillion times stronger than Earth's. If you wonder what this actually means, if a magnetar were as close to Earth as the moon is, all electronic devices on Earth would instantly fry. Credit cards, phones, computers, satellites, in short, nothing that maintains global order would function. Yet this would only be the beginning, because such a magnetic field affects not just technology, but directly matter itself. Atoms normally consist of electrons orbiting a nucleus, but under a magnetic field this intense, electrons can no longer remain in their normal orbits and are deflected. The magnetic field stretches and elongates them, causing atoms to deform into thin, needle-like strings. In other words, matter ceases to be matter in the sense we know it. The surface of a magnetar is one of the harshest environments in the universe. The surface consists of an incredibly dense and extremely rigid crust. Breaking this crust might seem impossible, but the truly fascinating point is that this crust can indeed crack. You can think of it like earthquakes on Earth, though making a direct comparison between the two is highly illogical. To give in scale, the energy released during a starquake on a magnetar can be equivalent to the total energy produced by our sun over approximately 100,000 years, and in some cases, it can be even more. During these ruptures, the magnetar blasts massive energy flares into space. These bursts are usually in the form of gamma rays, which is the most energetic type of radiation in the universe. For instance, in an event observed by astronomers in 2004, a magnetar located within the Milky Way experienced a giant flare. This explosion was of such monumental power that it managed to affect Earth's atmosphere even from a distance of about 50,000 light-years. An increase in ionization was observed in the upper atmosphere, which meant that the eruption of a distant star had actually altered the weather of our own planet. Another unbelievable aspect of magnetars is their surface temperatures. universe. Just like their rotation speeds and magnetic fields, their surface temperatures are monumental, generally varying between 3 million and 7 million degrees. For comparison, the surface temperature of our Sun is around 5,500 degrees. Try to visualize the immense difference in your mind. However, the truly interesting thing is this: magnetars do not become this bright just because they are hot. Their energy is largely derived from their magnetic fields, and this field decays over time. Energy is released during this process. So to speak, a magnetar literally uses its own magnetic field as fuel. The period when magnetars are most active lasts roughly between 10,000 and 100,000 years, and this is perhaps their weakest point, because when considering the age of the universe and evaluating it on a cosmic scale, this is a truly short lifespan. After this process, the magnetic field weakens significantly, and the magnetar finally calms down. The bursts decrease, and the star transforms into an ordinary neutron star. Yet, of course, even this calmed state version remains at extreme limits. I also briefly mentioned their rotation speeds at the beginning. As I said, due to their neutron star nature, magnetars can spin hundreds of times per second when they are born, but they slow down over time, eventually rotating just once every few seconds. Behind this deceleration lies, once again, the loss of energy from the magnetic field. So as you can see, the magnetic field functions almost like a heart for magnetar stars. Furthermore, magnetars occasionally experience sudden changes in their rotation speed. In the scientific literature, this is called a glitch, and the star suddenly begins to spin slightly faster. This phenomenon is generally associated with structural changes occurring within the star's internal composition. All of this information actually comes to us because scientists do not merely observe magnetars. They also use these stars to test the laws of physics in the universe, and therefore, we know more about these stars than many other cosmic structures. The reason scientists conduct these tests is that around these stars matter, and even the vacuum of space, cannot behave normally, leading scientists to view these stars as perfect laboratory environments. Besides, what we normally call a vacuum is not entirely empty. According to quantum physics, virtual particles constantly pop into existence and annihilate one another, but a magnetar's magnetic field is so powerful that this quantum process becomes observable. In other words, even nothingness behaves differently in the presence of a magnetar. One of the most fascinating recent discoveries regarding magnetars is their connection to fast radio bursts, FRBs. Millisecond-long radio signals are detected in the universe, and these are called fast radio bursts. Well, it is believed that the source of some of these bursts is magnetar stars. In fact, scientists directly observed such a signal originating from a magnetar right inside the Milky Way. If we look at the internal structure of magnetars in a bit more detail, we must start from the outermost layer. On the very outside, there is an extremely thin atmosphere, and this atmosphere is not actually a gas layer like the ones on planets we know. Its thickness varies from only a few centimeters to a few meters, but because its temperature is millions of degrees, it possesses an incredibly energetic environment. In this region, even atoms are not entirely stable. Beneath this atmosphere lies a crust, and according to estimated values, its thickness is around 1 kilometer. This crust is considered one of the hardest structures in the universe, and the matter here exists in a structure far denser than a normal crystalline arrangement. At this point, atomic nuclei are packed so tightly that they are almost touching one another. However, the truly fascinating part begins beneath this crust. In this region, a structure forms with the playful name of nuclear pasta. Even though its name sounds funny, it is a physically mind-blowing structure. The density in this region increases to such an extent that atomic nuclei can no longer maintain their spherical shapes. Instead, they form long strips, sheets, and tube-like structures that I mentioned earlier. Due to these shapes, scientists describe these structures with names like spaghetti or lasagna. The density in this region is billions or even trillions of times greater than the densest matter on Earth. Once we pass this region and descend even deeper, we finally reach the core. The core of a magnetar consists entirely of neutrons. However, these neutrons do not just sit there in an ordinary fashion. A certain portion of them exists in a superfluid state. That means they move without any friction whatsoever. At the same time, protons can form a superconducting structure. I know this part is a bit confusing, but to understand it more simply, the electrical resistance in this region is zero. This means the magnetic field can exist in this environment forever. At this point, a paradox actually comes into play because a magnetar's magnetic field is so powerful that it can disrupt even this superconducting structure. In short, even the laws of physics break down here, and physics begins to stretch its own boundaries. Additionally, an area called the magnetosphere surrounds magnetars. This field is similar to Earth's magnetic field, but is unimaginably stronger and more complex. When you look at Earth's magnetic field, you see a highly organized system, but around magnetars, this field is severely twisted. In other words, the magnetic field lines do not stand straight, they are twisted and strained. While this twisting interesting might seem like an insignificant detail, it is actually a massive factor because it causes colossal electrical currents to form around the star. These currents lead the star to continuously radiate energy. Let me give you another interesting fact. The particles within this field can accelerate to speeds close to the speed of light, and when these particles collide, high-energy X-rays and gamma rays emerge. At the beginning, I mentioned the explosions, or rather the crust ruptures, that occur on magnetars, and I also pointed out the high dose of energy these flares release. So what would happen if such an explosion occurred at a distance close to us? To summarize it in a single word, disaster. It wouldn't even need to be in an extremely close location. A magnetar flare occurring at a distance of about 10 light years would severely damage Earth's ozone layer. If it came to a closer distance, our atmosphere would be on the brink of eradication, radiation levels would surge monumentally to become lethal, and the entire ecosystem on Earth would collapse. This means magnetars pose a theoretical threat not just in deep space but directly to Earth as well. However, there's no need for us to be anxious for the time being, because even the nearest magnetars are currently located at a very safe distance from us. Nevertheless, the universe continues to surprise us every single day and reveal many things we are unaware of. Therefore, as humanity, we must still not lower our guard. Yes, friends, I hope I've been able to explain magnetars to you in a beautiful, understandable way, and I hope you enjoyed my video. If you liked my video, don't forget to hit the like button, subscribe to my channel to support me, and leave a comment to share your thoughts. Until we meet in our next video, take very good care of yourselves. Goodbye.